Okay, welcome to the Chapter 5 Homework 1 review, where we have our first exposure to topics related to moles. It's going to be an important topic for us in the next few chapters of this course, so this is sort of our first taste of that. Looking at the overall scores for this assignment, you guys did pretty well, averaged right around 10 out of 12, which is what we typically see for the homework assignments, so no drop in performance here. But there are a few different types of problems that we want to go over, and that's what I'll be covering today. One of them was a request from a student, and then the other ones are ones where the scores were a little bit lower on average for these types of problems. So the first couple I want to talk about are just related to mass percent, and in some ways this is a review because we introduced mass percent and mass fraction really close to the beginning of the course when we started talking about the law of conservation of mass and the law of definite composition. So those two mass laws really deal with mass percents on some level, and so we talked a little bit about that a few weeks ago, but now we're sort of bringing it back in a different context. So these first two problems really are just review of mass percent and don't even require us to know anything about moles. So some of you may have overthought what we were asking on these first two, but they're just dealing with mass fractions or mass percents. Alright, so this first one here, a mineral contains only lead and sulfur. If analysis indicates that a 6.25 gram sample of the mineral contains 5.41 grams of lead, what is the mass fraction of sulfur in the mineral? Alright, so to remind ourselves where we're starting, we have 6.25 grams of the mineral. We know that there are 5.41 grams of lead, which has a chemical symbol Pb, not that it matters here. And so if it's only contains lead and sulfur, that means the rest of the mass has to be sulfur. So the mass of sulfur then would be 6.25 grams of the mineral. That's the mass of the mineral. Minus 5.41 grams, which is the amount of lead that's in the sample, which comes out to 0.84 grams. Alright, so this is the mass of sulfur in the sample. And if we want the mass fraction, remember that mass fraction is just going to be the mass of that element, which is sulfur, divided by the mass of the compound. And because we're looking for the mass fraction here, we don't want to multiply by 100. Remember, we have, in a lot of different of these quantities, we have the ratio, which is called the fraction, and then ultimately we also express percents, which is out of 100, so we have to make sure we don't do that extra step here. So we're just going to take this ratio and be done. So the mass of sulfur we determined was 0.84 grams. The mass of compound that we started with, 6.25 grams, that's the total mass. And this comes out to 0.13. And presumably we instruct you to enter so many decimal places. I don't remember what the exact number was, but that's how we would report the answer here, just as 0.13. It could also be written as 13%, but here we just wanted the mass fraction, so we'd stop there. Sorry. So whenever we have binary compounds with two different elements in them, we just have to take the ratio of the element to the total mass of the compound. That's going to be the mass fraction for that particular element. Okay, so then we have one more problem that asks us to use mass percents, although this time it takes it a little bit of a step further. So we have an ionic compound that contains a metal M, which we're not even identifying, and bromine. If analysis indicates that a 10.3 gram sample of the compound contains 4.75 grams of M, what is the mass of Br? What mass of Br in grams is contained in 3.98 grams of the mineral? So this one takes it a step further because we need to first determine the mass ratio and then extrapolate it to a different amount of the mineral. So again, our starting point here, we have, if we have 10.3 grams, sorry, the compound, ionic compound in this case, not really a mineral, we know that we're told that it has 4.75 grams of M, whatever that metal is, and then the mass of bromine in that 10.3 grams is just going to be the difference of those two. So 10.3 grams of the compound minus 4.75, which is the mass of the metal. And so we get 5.55 grams of bromine. I'm being a little bit loose with significant figures here, but we don't want to do too much rounding at the beginning. Alright, so then we have so we can write some ratios over here. We have 5.55 grams of bromine per 10.3 grams of the compound. And this is going to be the key ratio. Now we could calculate the mass ratio and actually work it out, but really we don't even need to know the number. We can just use this ratio as a conversion factor. So how does that work? We want to know the mass of bromine in 3.98 grams of the mineral. So if we want the mass of bromine in that sample, we have 3.98 grams of the compound, or the mineral in this, as we call it. And then this ratio here allows us to convert between grams of bromine and grams of compound. So we want grams of compound to cancel. So we're going to put that 10.3 grams on the bottom. And for each 10.3 grams, we have 5.55 grams of bromine. And so this says in a 3.98 gram sample of the mineral, we have, let me work this out, 2.14 grams of bromine. I guess they wanted 3 decimal places, so really, technically, wouldn't enter this as 2.144, but if you have the first 2 decimal places, then it would still count your answer. Alright, so that's how we do this one. We can use these mass ratios then as conversion factors to determine how much of one element is contained in a certain amount of that compound. So the first step was sort of recognizing how to use this given information to form a ratio, and then from there we can use that ratio to extrapolate how much bromine is in 3.98 grams of the compound. Alright, so definitely review mass percent and mass ratio because it is a topic that we've reintroduced here. But the more important things that we talked about and the newer things that we talked about are going to deal with conversions involving moles, so that's what we're going to see now on the next few problems. So this type of problem is one that always gets students the first time they see it. And I didn't really go over one exactly like this in class. So we want to know here, what's the number of chlorine atoms present in 27.5 grams of chloroform, which has a formula CHCl3. And then when we have the answer, we have to determine the log. So we're looking for actual chlorine atoms. So if we're looking for the number of chlorine atoms, we should recognize that at some point we're going to have to use Avogadro's number. And we're starting with a mass. So remember that when we start with a mass, the first thing we can do is use the molar mass to convert into moles. So we have to find the molar mass for CHCl3, which is going to be the atomic masses added together. So if we pull up the periodic table here, where's that? So if we pull up the periodic table, the atomic mass of carbon, 12.01, hydrogen is 1.008, chlorine 35.45. So we add up all the masses. We have one carbon atom which has a mass of 12.01. We have one hydrogen which has a mass of 1.008 grams per mole. And then we have 3 chlorines, each with atomic mass of 35.45 grams per mole. So when we sum those up, we get a molar mass of, sorry I didn't work this out ahead of time, 119.37 grams per mole. Alright, so that's the molar mass of chloroform. So that would allow us to convert from grams into moles, but then we have a couple extra steps that we have to add. So if we're looking for the number of chlorine atoms, let's just start writing out the conversions to get ourselves there. So we're given 27.5 grams of CHCl3. We can use that molar mass that we just calculated to convert into moles. So remember, if we're going from grams to moles, we're going to divide by the molar mass, which cancels out grams and converts into moles. Now here, there's a couple different ways we can approach the problem. So one way to do it would be to say, okay, if we have moles of CHCl3 and we want to look for the number of chlorine atoms, we should recognize that from the chemical formula, this little 3 here tells us that there are 3 moles of chlorine for every 1 mole of CHCl3. Alright, so that's one way to do this. We convert from moles of CHCl3 into moles of chlorine. And this step here is the one that pretty much everybody forgets. Alright, so you have to remember that when we convert into moles, we're talking about moles of CHCl3 molecules, but if we want moles of chlorine atoms, you have to account for the fact that there are 3 moles of chlorine per mole of CHCl3. And then finally, to get into number of chlorine atoms, we have to use Avogadro's number. So 6.022 times 10 to the 23rd atoms of chlorine for every 1 mole. And that cancels out moles of chlorine and then gives us an answer of, let's see what we get. So I'll give you some time to work this out. 4.16 times 10 to the 23rd chlorine atoms. Now there is a slightly alternative way to think about this, although the mathematical operations are the same, so let me add a page and do that real quick. Alright, so another way to set this problem up would be, you kind of start it the same way. We're looking for number of chlorine atoms. So we have 27.5 grams of CHCl3. We first have to convert it into moles. That same first step is the same. So we use the molar mass again to get us into moles. Now from here, what we could do is we could use Avogadro's number at this stage and say that there are 6.022 times 10 to the 23rd CHCl3 molecules per 1 mole of CHCl3. So remember that this Avogadro's number tells us the number of constituent particles, or the number of things that make up that mole of sample. So if we have CHCl3, which is a molecular compound, we can use Avogadro's number to say that there are 6.022 times 10 to the 23rd molecules of CHCl3 per 1 mole. And then at this stage we can say the chemical formula CHCl3, another way to interpret that is that there are 3 chlorine atoms for every molecule of CHCl3. So we're multiplying by the same numbers, so we're going to get the same answer, but what we're doing here is just doing things in a slightly different order, thinking about it in a slightly different way. So either of these works, whatever makes more sense to you, you can do, but the key point is, again, don't forget to at some point account for the fact in this problem that there are 3 chlorine atoms per molecule of CHCl3, or alternatively there are 3 moles of chlorine per 1 mole of CHCl3. And the last thing that this problem has to do is enter your answer in log format. So remember, when we do questions in Blackboard, we'll usually have you take the log of the answer, if it's a big number like this especially. And so you get something like 23.62 is the answer you want to put into Blackboard. And I think this problem and many of the other ones in this homework assignment had a variable input. So this 27.5 grams was randomly generated. So you may have had the problem with a different starting amount of CHCl3, but the steps are the same to get to the final answer. And then this next question here is very similar in concept, except this time we're not even starting with a mass, we're just starting with the number of moles. So if we have 0.100 moles of ethane, C2H6, we need to know what does this contain. So answer choice A is a number of molecules, and then the rest of them are the number of atoms that it contains. So let's figure out how many molecules and how many atoms are in a 0.1 mole sample of C2H6. So the number of molecules is just a simple one-step conversion. We have 0.100 moles of C2H6, and then Avogadro's number would tell us that there are 6.022 times 10 to the 23rd C2H6 molecules per 1 mole of C2H6. So this tells us that we would have 6.022 times 10 to the 22nd molecules, which is not correct. So choice A is eliminated. That's the wrong number of molecules. Now let's figure out how many atoms are in this. And again, there's a couple different ways we can do this, but the number of atoms would be, if we start with this number here, 6.022 times 10 to the 22nd molecules, If we look at the formula C2H6, there are 2 carbons, 6 hydrogens. That means we have a total of 8 atoms per molecule. Okay, so C2H6 total of 8 atoms, so there's 8 atoms per molecule, which means the number of atoms is just 8 times this, which comes out to 4.82 times 10 to the 23rd atoms. And that matches then choice B up here. Alright, so remember that these chemical formulas tell us the number of each atom that's in one molecule, or the number of moles of atoms that are in 1 mole of the compound, and we can use those conversions to then help us in these types of problems. So I didn't really go over that in class, so this was a problem that we had a little bit of trouble with, and hopefully now we can see why we missed this for some of you. Alright, so then we have another few problems that deal with determining empirical and molecular formulas using masses or mass percents. So the first one here, we have a compound that's 10.13% carbon and 89.87% chlorine. Now keep in mind we didn't have to give you both of these mass percents. They should add to be 100. So if the mass percent of carbon is 10.13, then we already know that the mass percent of chlorine is 89.87 if those are the only 2 elements. Determine both the empirical formula and the molecular formula. Given that the molar mass is 237, type the molecular formula in the space provided. So when we're given mass percents, we can use those to determine the empirical formula. That's the first thing we always have to do. So if we have mass percents, we're going to assume 100 grams of compound, and then those percents just become masses. So if you have 100 grams of this compound, you have 10.13 grams of carbon and 89.87 grams of chlorine. And the first thing we always have to do when we want to determine an empirical formula is convert the masses into moles. So to find the moles of carbon, we have 10.13 grams of carbon, and then we use the molar mass, or the atomic mass of carbon, which is 12.01. Again, we can go find that on the periodic table here. It's atomic number 6, 12.01. And so when we divide that, we get 0.8435 moles of carbon. And then to find the moles of chlorine, we do the same thing with its mass. So the mass percent of chlorine is 89.87, which means 100 grams of compound has 89.87 grams of chlorine. And then the molar mass of chlorine, the atomic mass of chlorine, again, we used this one earlier, it's 35.45 from the periodic table. So 89.87 divided by 35.45, we get 2.535 moles of chlorine. And then finally, to find the empirical formula, we have to find the lowest ratio of those two. So C 0.8435, Cl 2.535. Neither of those are very close to a whole number, so we're going to divide both by the smaller of the two. And so when we divide those, we get C, and then we get Cl 3. And it works out pretty much exactly to a whole number, so we don't have to do any additional operations. Remember, we don't want to do a lot of rounding for these. But this comes out exactly as CCl3, and then the empirical mass is what we next need. So this is the empirical formula, but we want to find, for the final answer, the molecular formula. And so that's where we have to use the molecular mass or the molar mass to help us. So the empirical mass, actually I'm going to do this down on the next line. So the empirical mass we have to calculate first. It's the mass of carbon, 12.01, plus 3 times the mass of chlorine, which is 35.45. So So the empirical mass for this compound is 118.4. And then remember what we have to do here is we're going to divide the molecular mass by the empirical mass. So I'm running out of room again. I'm going to add another page. Alright, so we're going to take the molar mass, which is given to us, and divide it by the empirical mass. So the molar mass is given as 237. The empirical mass that we just found is 118.4. And so we should get a small whole number when we do this, and we get pretty much exactly 2. So when the molar mass is 2 times the empirical mass, that means the molecular formula is 2 times the empirical formula. Remember, empirical formula is the lowest whole number ratio, but the molecular formula tells you what's actually in the compound. So if we take this empirical formula CCl3 and we double it, that's going to give us the molecular formula of C2Cl6. Alright, so that's the molecular formula for this compound. Now last step again, we had to compare the molar mass that's given to us to the empirical mass, and we find that the molar mass is twice the empirical mass. That means the molecular formula is twice the empirical formula. Alright, and then a related concept is combustion analysis. So here is another type of problem where we're going to be finding empirical formula, but again in this case we're going to first have to extract the masses of each element. So in the previous problem I gave you directly the mass of chlorine and the mass of carbon, but then we wanted to find the empirical formula from that, but here we're not given those masses directly. We have to first find the masses of each element. Alright, so remember that when we do combustion, we have a compound here that consists of CH and O. So we have some subscripts X, Y, and Z. We don't know the formula to start with. And then when we do combustion, we burn that with O2 in excess, and we make some amount of carbon dioxide and some amount of water. And so the key point here is we can't really balance the reaction because we don't know the chemical formulas, but we do know that all of the carbon in the sample goes into CO2. All of the hydrogen in the sample that we're burning goes into H2O. Oxygen gets distributed everywhere, so we're going to find that last by difference. So we first have to find the mass of each element. So what we're going to do is find the mass of carbon first. We have 100 grams of sample and we produce 70.6 grams of carbon. Now in this case, I guess I got ahead of myself here. We're actually giving you the masses. We give you the mass of carbon and the mass of hydrogen from water, so we don't even have to do these calculations. So really this was worded in a kind of a roundabout fashion, but we didn't even need to really do the extra step here to find the masses. So there are some cases where we'll give you just the masses of CO2 and the mass of H2O, and you'll have to pull out the masses of each element, but we didn't even go that far here. So 70.6 grams of carbon, that's given to us, we don't even have to calculate it. The mass of hydrogen is 5.92 grams. And then remember that for the mass of oxygen, we can just use whatever's left. So for the mass of oxygen, we know that we have 100 total grams of the compound, and so that's the mass of the compound. Sorry, we're going to subtract the mass of carbon, which is 70.6. We're going to subtract the mass of hydrogen, which is 5.92, and so that leaves 23.48 grams of oxygen. Okay, so we have masses of all the elements now, so we're going to do the same set of steps we did last time. I'm going to insert another page because I feel it's going to take more than one page. I'll do that now. Alright, so we're going to find the moles of each element. Moles of carbon, we have 70.6 grams of carbon. The atomic mass of carbon is 12.01. So we get 5.88 moles of carbon. Moles of hydrogen, we have 5.92 grams of hydrogen, and we use the atomic mass of hydrogen, which is 1.008, to tell us we have 5.87 moles of hydrogen, so pretty much the same. And then for the moles of oxygen, we have 23.48 grams of oxygen. The atomic mass of oxygen is exactly 16. You can verify that from the periodic table. And we get 1.468 moles of O. Okay? So you have moles of each element, and now we can then go and determine the empirical formula by finding the lowest ratio. So we have C 5.88, H 5.87, O 1.468. So when we divide all of these by the smallest, so the smallest is oxygen, which is 1.468, we divide all of those molar amounts by the smallest one to get the lowest ratio. What we end up with is C5HW1Review. And we don't have to do anything else. Now again, remember, we don't want to do too much rounding here, so if we want to be a little bit more precise, what we get is we get C 4.01, we get H 4.000. So because this 4.01 is pretty close to a whole number we can round, we don't want to do too much rounding in these problems. If it's more than, let's say, 0.1 or so, we don't want to round it. But here's really close. We can just round to C4H4O. Alright, so this was again a pretty typical problem. We set it up as a combustion analysis problem, but we gave you the mass of the elements directly, so that turned it into a pretty straightforward problem, but a lot of steps because we have 3 elements in this case. And then finally, the last one I want to go over is this one was requested by a student. There was another one very similar to it that we had difficulty with, so I'm happy to cover this one as well. It's one of our first unknown element problems. So we're going to see a lot of different problems coming up in the next few chapters, especially where we ask you to identify either an unknown element or an unknown compound. And almost always when you're doing this, what you want to find is the molar mass of that element or compound, and then match it to either an element from the periodic table or to a molecular formula in the cases of molecules. So here we're trying to identify the element M, and so anytime we want to identify an unknown element, we can find its atomic mass, which is really its molar mass. So remember, the definition of atomic mass is the grams of M divided by the moles of M. So if we can find both of these parameters, the mass of M in grams and the number of moles of M, we can then calculate its atomic mass and then allow us to identify it from the periodic table. So the mass of M is going to be pretty straightforward because that comes from the mass percent. Remember, if we're giving you a mass percent, we can assume 100 grams of compound. And so what we're going to have is 19.66 grams of oxygen, because that's the mass percent of oxygen, and then we're going to have, for the mass of M, it's going to be 100 grams of compound minus 19.66 grams for oxygen, which is going to be 80.34 grams. So we got the first number already. So if there's 19.66% oxygen, there's 80.34% metal. If we assume 100 grams, that means that our sample has 80.34. we have 80.34 grams. Now if we're assuming 100 grams of compound, we can then also find how many moles of M there are. And so this is going to be a series of conversions where we know that our 100 grams has 19.66 grams of oxygen. So if we know that there's 19.66 grams of oxygen in the sample, we can convert that into moles because we know the atomic mass of oxygen. So the atomic mass of oxygen is 16. So that's the moles of oxygen. We want to find the moles of metal. Look at the chemical formula. The chemical formula is MO. That means there's equal numbers of moles of M and O, which means for every 1 mole of oxygen, we have 1 mole of M in the sample. Alright, so from this conversion, we find that 100 grams of our compound has 1.23 moles of metal. So if we divide these two, 80.34 divided by 1.23, we get 65.3 grams per mole. And if we go to the periodic table, we want to find the element that is closest to 65.3. It looks like it's going to be zinc, which is 65.4. So the atomic mass that we determined by dividing the mass divided by the moles most closely matches that of zinc, Zn, so that's going to be our unknown element. So that means the identity of M is going to be zinc, Zn. Alright, so we're going to see other problems like this in the future where we ask you to identify unknown elements, and what you really want to do in these cases is find the atomic mass of the element, which if you can find the mass of that element in the sample and you can find the number of moles of the element in the sample, you divide the two to get the atomic mass. Alright, if you have any other questions on this homework assignment, please feel free to contact me either by email or coming to my office, and I'll see you next week with the next Chapter 5 homework.